First off, I want to go over a problem that on an assignment that I just gave back. Is that one it had like the spring, and you drew the graph like this, and you had like a certain force, and you had a certain elongation, and you all found the slope perfect. It was like 19.6. But then it said the next question on B was like, how much force does it take to stretch it to a certain distance? Okay. And what you all did is that you all, for the most part, used, work equals force times distance. Okay, and you treated it, like I said, and you all treated it like a rectangle. Like it was the same amount of force exerted over that distance. It's not. Okay, it's a spring. Yes, you do have to find the area underneath the graph. But that area is a triangle. It's not a rectangle. Okay? So that's one way you can do it, is you can find that area legitimately. Cool, it works. Okay? The other thing that you could have done is that you could have used us equals 1/2 kx squared. Either way, you're going to get the same answer. But you don't get that answer if you use force times distance, because it's not that same force acting over that entire distance. Okay? So that was without doubt the most missed question on that assignment that I just gave. Okay? You have, on a spring, okay, that's being compressed, it's not the same force acting over that distance. The farther you stretch it, the more force it takes. That's why it's a linear function. Okay, so let's chit-chat about some of the problems out of the book, like 1 and 3. Okay? So, we got 10. Let me just go get some ring stands. I'll just bring everything up. That's just convenience.
Number 8.
Why? Did you fix it?
You didn't square the
How
velocity.
did you get 9.9 on that one?
Oh, I didn't?
1/2 mv squared, and you didn't square the velocity.
okay. Thank you.
Hang on, why did you?
You're clutch for that.
Why did you do that one?
What?
Why'd you use this equation?
I don't know. Felt like it. Which one did I not square the V, Paul? The first one or the second one?
Number 8.
Both?
Yeah,
Oh, shoot. You're right.
it should be the same.
You're right. 2.40. Is that the only one?
That's the only one I found. Everything else I agreed.
Nice.
Why did you use that equation for number 1?
Which one?
Why did you use that? Why'd you use this one instead of this one?
Why'd you use that equation?
Number what?
Well,
Number 1? We didn't use that equation.
use that one. No, I'm not.
Okay.
Equation, I mean that one.
Yeah, I didn't
So,
use that one on number 1.
Here's the setup that I have up here.
Both of them on number 1.
So what I've got is I've got two scales holding up the meter stick, right? So right now, what do all the forces have to add up to?
Zero.
Zero. Why?
Because it's stable.
Stable, right? Everything's in equilibrium. So if I was just holding up the meter stick with one scale, what would the reading on the scale be equal to in terms of the meter stick?
The meter 6
Just
weight.
the weight of the meter stick, right? Right, just one scale would be that. So, because the fact that this is where it kind of goes back to when we did like force vectors, it's a similar type idea. So now I've got two scales, right? So if they're each carrying, if everything's symmetrical, they would each be carrying half the load. Okay, and that's if you look at, they're both at about 0.5 right now. But if I take and hang this scale, or take this 200 gram mass and hang it down from here. So here's what I want you to look at. So right now, I've got that 200 gram mass here. The reading on this scale is 2.02 newtons. And the reading on that scale over there is like 0.85. Okay? So think about this. Look at all the dynamics that are happening. So I've got this force going up. I got this force going up. Those are the only two forces that are acting up. But I've got this trying to pull it down, and I've got the center mass of the meter stick itself that's trying to pull it down. But if I add everything together, everything should still add up to zero. But the interesting thing happens. What do you think is going to happen if I move that scale, if I move this mass over here?
It's gonna shift the weight to that one.
Yeah, so if I move this over here, okay, now what's going to happen is that this has gone up to like 2.12, and this one has gone down to 0.77. So depending upon where I distribute that mass, that's going to impact the reading on these scales. But no matter what, everything still has to add up to equal to zero, okay? Because the system's in equilibrium. So depending upon where you put that weight, that changes the reading on the scales. Got that idea? Mm-hmm. So here's the other important thing. I've got these forces going up, and I've got some forces going down, okay? But everything has to add up to zero. Okay, got that visual? Sure. All right. So, try and definitely move this over here. So if you look on problem number 1, okay?
It was off. Alright.
So you've got these two scales like this, okay? And you've got, what's the weight of this thing? Huh? 627?
Which one are you looking at?
Problem number 1 out of the book.
Oh yeah, I think it was 64.
64 kilograms.
Yeah.
Which if you multiply that by G, you're going to get okay. So this length is 1.5 meters, right? So that's an entire length. And you've got two scales, and the person is standing here. Okay? So Bubba's standing there. And that's going to be 1.5 meters out of that entire 2-length meter thing. So here's the basic idea, right? So that mass is 64 kilograms. If you take 64 kilograms times G, you get 627, right? Mm-hmm. So that's going to be a downward force of 627 newtons. So that means that these two forces over here, call this N1, call this N2, those two forces acting up have to balance out the 627 Newton force acting down. And that's all going to add up to equal to 0. So if you set it up that way and go, this is going to be the reading on scale 1, call it number 1, plus 2, plus negative 627, all those together have to add up to 0, right? Mm-hmm. At this point, could I solve the equation?
No,
Why?
because you don't have enough
Yeah, I have two variables and only one equation, okay? Now, this is where the next part of this comes into play, basically in terms of torque. So if you look at what's happening, so if you consider this thing pivoting around here, so what's happening, if you think about it, this weight is trying to drag this thing in this direction, okay? Like it's creating a torque. This one over here is pushing it up. So this one out here is pushing it up. This one is pushing it down. If you consider it trying to pivot around this one. So this one's dragging it down, that one's pushing it up. So what do you think has to be true with those two values? They have to be equal, okay? So here's the next thing you can do. Okay, so I'm going to get my second equation, I'm going to take negative 627 newtons times 1.5 meters, okay? Now, that has to equal the reading on that second one times 2 meters, Now, at this point, could I find the reading on the second scale? Yes. So then once I get N2, then I can put N2 up here, then I can solve for N1. Okay? Pop?
So how'd you get that last equation?
So basically, here's the story. So this is creating some torque coming down here like this, right?
Yeah.
Okay? Because if you just leave this out, that guy standing there is going to be creating a torque which is going to try and pull this board down this way.
Oh, so you know the torque created by the scale has to be the
Yes.
same. Okay.
And then this scale over here has to balance that out.
That torque.
Yes.
Okay.
Okay?
Oh, and then just
That makes
whatever's left over is N1.
Yes.
Okay. Gotcha.
Bingo.
Does that make sense?
Yeah. It makes so much sense when you do it, but when I'm actually looking at the
I know.
it's like, what do I
That's
do?
you make it look so easy every time.
It-
I'm
it feels so
like,
easy
whenever
when
you
you-
explain it. I'm like, oh, I understand this, and then later
Okay.
I go and do it, and I'm like, what? How do you do this? I'm like,
Okay.
I think I was stuck on
I've
number
kind
2
of
for
been
God
doing
or
it for a
something.
while, so it's like if I
Yeah.
couldn't explain it, then I really suck. So, you know, that's the other reality of it. Okay, now, number 3 is actually a little bit more complicated. So this is what I tried to show you yesterday with like the boards, okay, to get that concept. So on number 3, here's this table, and here's the legs, and Bubba is standing out here on the edge of the table. But it's a similar type idea, right? So he's going to create some torque which is going to try and make this table spin in that direction, right? This, because it has mass, is creating a torque in that opposite direction, okay? So if he goes out too far, that torque is going to tilt the table this way, okay? So what we want to do is find that exact point where those two balance out, okay? So what you're trying to find. So you're told that this is 0.55 meters. So it's like a fulcrum, okay? So that's 0.55 meters. And you know that he has a mass of 70 kilograms, and the table itself has a mass of 56 kilograms. So imagine that you've got a 56 kilogram mass pulling down this way, and then you've got his 70 kilogram mass going out here like this, okay? And so what you're going to try and figure out is that where is this thing going to balance out, okay? So this is this whole concept of center mass. It's like you're going to take all of the mass of that table and you're going to concentrate it right there, okay? And like if you could do the deal like I showed you yesterday, like if you could take your fingers and put that underneath the table and slide that, that's where that would meet, is underneath that exact center of mass. So you have a torque going one way and you have a torque going the other way, right? Everybody get that concept?
Yeah.
So if his torque gets too big, the table is going to go in tilt. If he's inside that distance, the table is going to win. If he goes beyond that distance, he's going to win. So we want to find that break point where it's just going to balance out. Okay? So that is going to be, that from the table is going to be 56 kilograms times G. Now you got to have that distance. So that distance, if you think it through, because that's 2.1 meters, that means half that distance is 1.05 to get to the middle. But you need the distance from the leg that it's going to pivot around. If you do that math, that's 0.50 meters, okay? Because that's going to be the distance from that leg. Now, that has to equal his 70 kilograms times G, and that's your unknown value, okay? So X is your unknown, okay? So at that point, it just turns into an algebra problem. Okay? But the whole idea being is that you have to have that idea that the center of mass of that table is concentrated at that single point at a distance of 0.5 meters from where that table is going to pivot around that leg. Okay? Does that make sense? Okay. So when you get to those questions like 16, okay, two children walking along, carrying, total length is 1.8 meters. So if you've ever lived in Africa, you see this happening all the time. And the older child supports twice as much weight as the younger child. How far is the bucket from the older child? Okay, so here's the older one. Here's the younger one. Now, just think this through. Where are you going to put the bucket? Closer to the older kid, closer to the younger kid?
Older.
Closer to the older. So you know that distance has to be closer. Okay, you know that has to be true. So basically, let this distance be x. Okay, this is it's almost like a Lagrange problem. But they want to carry twice the force. So you're going to have twice the force times x is going to equal what?
The force times like another y, basically.
Well,
Or
what's,
1.8
if this is
1.8
x,
minus
how
x.
much is left over?
1.8 minus x.
1.8 minus x. Then what are you going to have to do?
Solve for x.
Yeah, so you got to distribute that force, get all the forces on one side, get the x's on the other side, and solve for that. So that answer on 16 should be around 1. How about that? If you do the math.
She left.
Any score in the game?
Goal!
I timed that one right.
Just
Get-
did. That's crazy.
This allowed?
Yeah, that was actually a good guess because I looked over and I was like, they're in the box.
Is that
Yeah.
offsides?
Man, that timing was insane.
I know. No, I really.
Any
just
score
looked
on
at
the
I'm
it.
listening to it in my ear.
He's got an earpiece.
No, I don't.
I
He's
think
the
they're
coach.
gonna call it offsides.
Are they really?
Oh, he's
No,
hurt.
I don't like him anyways.
Delicic?
Yeah, I don't like Pulisic.
Why?
Every
Okay.
time he touches
you're
the ball,
well.
they're like, oh! He's
Yeah, because he's good.
no,
You're a
like
Welsh
third
op.
string Chelsea.
Now-
That was a good ball.
Let's
know.
talk about on that multiple choice question number 1.
Let's go.
Okay?
So much for going crazy.
Because that's a good question because it ties in a whole bunch of stuff.
Crazy.
So the one thing that I don't spend a lot of time talking about, mainly because it just you can get bogged down in it, is uncertainty in measurement. Okay? And that's just the reality of things. When we measure things, you know, like you look at the mass of an electron, you look at the gravitational acceleration due to, or the acceleration due to gravity. Okay? In reality, whenever you measure things, there's some uncertainty in that. Okay? And typically how that's written is a plus or minus value. So if you look on that question, it's got card A, okay, moving at 3 meters per second, plus or minus 0.2. So what that means is that you measure that as 3 meters per second. That reality is that there's some uncertainty in that. It could be 0.2 meters per second faster than that. It could be 0.2 meters per second less than that. So in reality, that can be somewhere between 2.8 meters per second up to 3.2 meters per second. Okay? We say it's 3, but in reality, somewhere between 2.8 and 3.2. Okay? That's our uncertainty. Obviously, the better the measurement device is, the smaller that uncertainty becomes. Okay? Got that idea? So the beauty of this problem is that it's also a momentum problem. Okay? Now, this is going to be a California problem, right? So, what's going to happen to the mass after the collision? How much is that mass going to increase by? Jackson?
It's gonna double.
Why is it going to double?
Because they're the same.
Yeah, they're the same. So we're going to double the mass, which means the velocity has to be half as much, which means this could not be a perfectly elastic collision because they're going to move off together. So basically, that means our velocity has to be half as much. So we're going to take this and divide this by 2. We're going to take and divide that by 2, which becomes 1.4 meters per second and that becomes 1.6 meters per second. So after the collision, then our uncertainty measurements is going to be somewhere between 1.4 and 1.6. Okay? So that's how you do that first question. Okay? Now, when you get to question number 2, okay? The whole key to question number 2 is that it's moving with a constant speed. Okay? It's not accelerating. Okay? You can get into what we call moving frames of reference. And if you're moving with a constant velocity, that's not bad. Where it gets ugly is when you have like accelerated motion and then you have accelerated frames of reference. That gets real complicated real fast. So basically, this thing is moving along at a constant velocity. So what you want to keep track of is the center of mass is, barring any external forces, your center of mass remains at the same location. Okay? So keep that in mind when you're answering number 2. Now, when you get to question number 3, okay? Here's this spring, right? And you've got your K value, 500 newtons per meter. Did they get to keep the goal, or did they waive it off?
Kept it. Kept it.
Okay.
Good.
Well, because you were talking, it might have been like offside, so.
I wasn't sure.
No, that was good.
Okay,
Pretty cool.
so imagine this. You're holding this weight, and you're going to lower it down, and it's going to change from 30 centimeters to 20 centimeters. So are you going to store energy in the spring? Yes, because you're compressing it, right? Because it's a spring, how do you calculate your US value?
1/2 kx squared.
1/2 kx squared. Okay? So you know the K value, you know it's going to go from 30 to 20, so you know how much energy you're storing in the spring. Now, is your UG value going to change?
Yeah.
Yes.
Yes. So think about this. You're increasing the energy stored in the spring because you're compressing that. But you're decreasing your UG because you're lowering the weight. So in this problem, and on this one they round it. So a lot of times, like on tests like this, standardized test, they'll round G to 10 meters per second squared. So that's what they did on this. So this is why, if you look at this in terms of like the actual numbers, they actually used that G to be like 10 meters per second squared. So that's why it kind of works out nicely. So what you want to look at is how much your UG changes, how much your US changes, and then look at the difference between those two. Okay? When you get to question number 5, okay, let me explain something about what's going to happen on number 5. And it's kind of a cool algebra trick. So this rod is going to move. It's about a fixed point, right? So when things spin, you have to talk about angular momentum. So start with the idea that L equals I omega, right? Now, here's the basic idea. This is just a broad idea. Any I, as a general idea, is mr squared, right? Cool with this, mr squared. Now, you also know that V equals R omega. True? Old school. V equals R omega. So if I solve for omega, I get V over R. So if I substitute V over R into here, I lose one of the R's, so I get Mr. V. Okay? So L equals Mr. V. Now, here's the deal. What do you get, if you arrange this a little bit, you get MVR. Well, what do you get when you multiply mass by velocity?
Momentum.
You get momentum. So you can also write this as L equals linear momentum times R. Okay? If you do a little bit of substitution. Now, here's the deal. The whole key to this question is that the ball is going to bounce back. So right away when the ball bounces back, what do you know about the velocity? Is the velocity going to change sign or not change sign?
Change
Change
sign.
It's
sign.
going to change sign, right?
Yeah.
So here's the deal. If you just even wanted to put in some numbers, okay? When I did this problem, I said, okay, I like numbers. So I said, okay, this thing is going to come in at, say, 10 Newton seconds. Okay? I just made up a number. Call it 10 Newton seconds. It's going to come in at 10 Newton seconds. Got to put it at 100. I just picked 10. Okay? Now, the whole key to this, it comes in a linear momentum of pi, and then it rebounds along its original line of motion with a momentum of pf. Okay? So notice that the momentum going in is the same as the momentum coming back out. But what's going to happen to that momentum?
Change sign.
It's going to change sign. So it came in at 10, it's going to leave at
Negative.
negative 10 Newton seconds, right? Now, look at when you look at change in momentum. Change in momentum, right,
P minus.
is P minus PI. So in this case, I would have a final momentum of, so look at that. Basically, what does it do? It gets doubled because of the fact that it's going to complete the reverse directions. So keep that in mind when you answer number 5. Now, let's talk about some of the questions off of my stuff, okay? On number, and I wish I could say I had this planned, and I was clever, and I spent a lot of time doing these calculations, but I can't. They just randomly work out this way. Every answer on number 4 should start with a 4. Okay? That's why I said I wish I was clever and I worked this out. Okay? And I got done, it's like, oh man, that's cool. I didn't plan it that way. Okay? But every answer to number 4 is going to start with a 4, and better yet, your answer to number 3 starts with a 3. And your answer to number 1 is going to be round 1.
Whoa. Every answer in number 4 starts with a 4?
Every answer on number 4 starts with a 4.
Every single one?
Every one of them starts with a 4.
Oh, no.
How?
Is that a problem, Bob?
That's a big problem.
Yeah, C through E. I got.
Okay,
through E,
let's
I got
start with
different
4A, because if 4A is wrong, everything is going to be wrong. What do you have for your answer to 4A?
40.
That's cool.
Good.
That's cool.
And then 400?
And then 400.
2.4 times 10 to the
Nope. C is your train wreck.
What did I do wrong?
How'd you calculate the moment of inertia?
1/2.
The moment of inertia, 1/2 mr squared,
Yeah.
which would be...
But, so your KR is 1/2 I omega squared.
Oh,
Oh, it's I omega squared?
Yes.
that's why.
I thought it was omega I squared.
I thought it was m omega squared.
No, it's I omega squared.
Where'd that come from?
I never.
Right there. Behind the meme.
Behind that equation.
Yeah, behind that.
Or it's also on your equation sheet.
Oh, it is?
Yeah.
Oh, okay. That's my bad.
That equals.
Number 1, I don't know. Number 1, I'm...
1 is old school momentum.
Yeah.
Bro,
What answer is it, like 1?
It should be around 1.
I said that.
Okay.
Dude. 7.
I'm.
Okay, I used.
You got the wrong answer.
Yeah, no, I used the.
It's not an elastic...
I used an elastic plate.
No. This is old school. This is not a collision. Okay? Number 1 is not a collision.
Okay.
It is so not a collision. Because look, what's happening
Sort of
is
a
that you've got,
collision.
was it Timmy and a rock?
Yeah.
So they're at rest. Timmy throws the rock in one direction. What's Timmy in the boat going to do?
Go in the other direction.
They're going to go in the other direction. That's why this is.
So you have to.
Perfectly lack collisions would be Timmy is here with the boat, and the rock hits him, and the rock bounces off Timmy.
Oh.
So, how close to 1 should it be? Because do you subtract the rock,
0.901.
the mass of the rock back out from the mass of the boat in Timmy.
What?
Yeah, because
Yeah,
his
'cause
he's
he
no
threw it
longer
out.
part of it.
Okay, because, yeah. You didn't do that, did you?
Oh,
You didn't do that. You didn't think it through?
get in. Oh, get in. Get in.
Another goal?
No, it was just allowed.
that
Yeah,
way?
I figured it. It seemed a little.
Okay.
That way?
Seemed a little far. I don't know.
Now, let's talk about number 10.
Get in.
So this is kind of a cool calculation.
Oh, no way.
So this is not to scale, but here's the Earth and here's the Moon. And you're going to try and find the center of mass of this.
Yeah.
So center of mass is going to be the mass of the Earth times some distance plus the mass of the Moon times some distance divided by the sum of masses. So if you're clever, what are you going to let the distance of the Earth be?
0.
0. Okay? Make it 0. There you go. By the way, where do you think the center of the mass is going to be? Closer to the Earth or closer to the Moon?
Closer to the Earth.
Closer to the Earth, right? So, if you do this right, you get an answer less than the radius of the Earth. Okay? Which is cool, and I'll tell you why. So the center of mass is right there. You wouldn't think the center of mass between the Earth and the Moon would be inside the Earth. You would think that center of mass would be like out in space in between the two of them. That would seem reasonable. It's like, oh, here's the Earth. The Moon's a long way away. Center of mass should be somewhere out in that space. Okay? In reality, that's inside the Earth. Now, here's the cool thing about this. Orbital two-body objects orbit around their center of mass. Okay? So everybody says, oh, Moon orbits the Earth. It does. But in the bigger scale, this whole system is orbiting the Sun. So what actually orbits around the Sun is that center of mass. So if you look at this in terms of here's the Sun, here's the Earth, here's the Moon. It's that point which is orbiting around the Sun. So yes, I'm not denying the Moon orbits around the Earth, but this whole system is orbiting around the Sun, and it orbits around that center of mass. Now, if that center of mass had actually been in between, our orbit would be much more complicated, because then it would be moving in a complicated, almost like figure 8 pattern around like this. So it's a good thing we have the Moon, because there's been any number of studies that said if we didn't have our Moon, we probably wouldn't be here having this discussion. Okay? Moon creates tides. Okay? So if you look at the evolutionary process, this is where physics meets biology. So because we have tides, and you look at the formation of life, which they think started in shallow waters, because we had tides, that tide was always causing an exchange of water along the coast. So you were always bringing in fresh nutrients. You were always bringing in fresh water, which they think aided in the evolutionary process of life. It also stabilizes our orbit, okay, because of the fact that that Moon is out there. We have a stabilized orbit. The Moon also, if you look at the surface of the Moon, it's very cratered, which means a lot of potential meteorites that might have hit us, the Moon basically took one for the team, okay? So they hit the Moon instead of hitting us, okay? And it's just cool that we have a Moon. So that's actually been theorized that if we didn't have a Moon, we might not be here having this discussion. So it's kind of cool that we have that. So anyway, your answer to number 11 should be, this is an ish around 0.5.
Number 11?
We'll take that. Not all day.
Okay? Are we good?
Yeah.
Wait,
Going once, going twice?
I have a
So,
question.
what?
So for number 4C,
Yeah?
4.80 times 10 to the third.
Perfect.
Let's go.
Better now?
Yeah.
Thank God I gave you some hints.
That's 3 wrong points right there.
Oh, that would have been a train wreck.
Yeah. Big train wreck.
Do you need us to show work on these? Okay. Cause I was about to say that, like, I don't think there's any way to show work
Which ones?
on these.
Timmy is strong as. Jeez.
Some of them there are.
How do you prove number
Timmy
4?
is a strong kid.
Huh?
How do you prove number 4 though?
What do you mean? Prove it.
On the multiple, or just how does that work?
What's number 4?
That's when he explained.
No, when you walk on the.
Yeah, so the center of mass remains at the same point. So
Okay.
the easiest thing to do is like count the divisions, figure out where the center of mass is, and then make. I just made a mark on the piece of paper and said that's where that center of mass is going to stay. That's how I.
Thank you.
What about
He
it?
said going once.
How do you go about that?
On mine,
About
Yeah.
that? How do you do that?
force times time equals change in mass times velocity. Remember what I did yesterday with the balloon?
Yeah.
Same idea.
What?
I don't remember. Okay. So force times.
What, number 2?
If it just slides, it only has translational kinetic energy, right? If I just make it spin, then it only has rotational kinetic energy. But if it rolls and moves, it has both. Makes sense?
Both.
Okay, so it's possible for an object to have translational kinetic energy and rotational kinetic energy at the same time. So, that total energy, the sum of those energies, is going to be my KT plus my KR. True?
Yep.
Cool with this. So, this is going to be 1/2 mv squared, old school, okay? I've got my velocity, I can do that part of it. Rotational kinetic energy is a problem because KR is 1/2 I omega squared. Now, the omega part isn't bad. Okay, excuse me, my I isn't bad. Because it's a solid cylinder, right? How do you calculate the moment of inertia of a solid cylinder?
1/2.
Now, this is going to be the classic example that you do not put in units, or excuse me, you do not put in numbers until you get to the bitter end, okay? If you try and put in numbers, you're going to go down a rabbit hole of pain and suffering from which you cannot escape, okay? You work with variables first. So this is going to be 1/2 mr squared. Now at this point, did I give you the radius of the cylinder?
No.
No.
It's 2 pi, right?
This is why I said, if you try and do it with numbers, you can't do it at this point. You don't know what the radius is. You're going, Burkamp, how do you expect us to do this? This is where the magic happens. This is the most important step on this problem. You all know that V equals R omega.
It does.
True?
Very.
If you solve that for omega, what would you get?
V over R.
V over R. Could I substitute V over R into omega squared? And then if I did that, I would get V squared over
R squared.
R squared.
R squared is cancel.
Ooh, this is punchy. What happens to my R squared?
Oh my gosh.
Cancel.
Wait, whoa.
So it's just MV squared.
Wait, doesn't it just cancel?
The R squareds do.
I know, but since it's V equals R omega, doesn't it, if you substitute
Hold on.
that in, doesn't it just cancel?
Hold on.
I've made a mistake.
You're getting a little bit ahead of yourself here.
Very confused on this.
Now, when I take 1/2 times 1/2, let's go old school fractions. I get
1/4.
1/4 M
That's 2.
That's a 2.
That's 2. That's a 2.
1/4.
Yeah, there it is.
I was thinking.
So 1/6.
So if I take 1/2 plus 1/4, I get
6.
I have no idea.
4 over
6
8
over
plus
8.
2 over 8.
What?
6 over 8, which is
3
over
fourths?
4. Yeah, 3 over 4.
what's 50 cents plus a quarter?
75. Sorry, I can't calculate tips either.
Who
It's
said
kinda
1/6?
That's a joke.
24 is MV squared?
Yeah.
That's why I didn't give you the
Mass.
radius.
Oh.
I gave you the mass, you have to know that one.
Hang on, you did.
Okay? So I'm going to take 3/4 times 1 kilogram times 1.8 meters per second squared, and you get
About
2.4.
I'm still a little confused on how the R's cancel.
One's in the
Because-
numerator, one's in the
I understand that, but omega equals V over R, right?
Yeah.
And omega's getting squared.
Oh, okay, I see what you did. I thought you substituted omega for V over R, and then it's V equals R, V over R. I don't know.
No, because it gets squared. That's where
Yeah,
it cancels
okay.
out. Okay? Got that?
Got it. Okay.
So that's why I said if you try and work this problem with numbers, it's not going to work. Okay? Now, here's what I don't want you to think. Oh, this is how I'm going to do every problem. It's just going to be 3/4 mv squared. It's not. Because depending upon, the process will always be the same. But what changes is that moment of inertia. So if that had been a thin hoop, that would have just been mr squared. If it had been a solid sphere, it would have been like 2/5 mr squared. So don't look at this and go, oh, total kinetic energy is just going to be 3/4 mv squared. It's not. What will always be true is that substitution. Okay? Got that idea. All right, now, bring the camera, let's go to the back of the room.
I'm still confused about two.
Detour.
what?
Just point the camera at the screen so you can watch it later.
I still don't know how to do two.
What?
Put it in the screen so you
How'd
can
you
watch
do
it
number
later.
two? USA.
Okay, we're good?
Hopefully.
Okay, so here's the deal. I have a baseball. When I let go of it, what's it going to do?
Roll.
It's going to begin to roll, right? So when it's up here, what's the only type of energy that it's going to have?
Potential.
Potential. Now, when it gets down to the bottom, what two types of energy is it going to have?
Kinetic.
Kinetic,
And
rotational, and
It's going to have KR and it's going to have
KT.
KT. Now, if this was the magic frictionless baseball, and this was the magic frictionless ramp, when I let go of it, what would it do?
just slide.
Yeah, it would just slide. It would only have
KT.
KT at the bottom. Okay, there would be no KR. Because things don't want to spin unless you create a torque. But because there's friction, when I let go of it, it gains both. So this is going to be important. It starts up here at pure UG, right? But when it gets down to the bottom, it's going to have two different types of energy. It's going to have KT and it's going to have KR. Now, what if I just hold it at the top of the ramp and I just drop it? So if I just hold it at the top of the ramp and I just drop it, what's the only type of energy would it have when it hit the bottom?
KT.
Just KT, right?
Yeah.
So if I just drop it, it's just going to have KT. If I let it roll, it's going to have KT and KR. So in which situation, think very carefully before you answer this, in which situation is it going to have more energy?
Equal.
They're equal.
When it hits the ground, falling, or it hits the ground, rolling?
They're the same.
It's the exact same. But in which case are you going to have a higher linear velocity?
That one.
When it rolls down
Oh,
or when it falls?
Rolls.
Rolls.
How many vote is going to have a higher linear velocity when it rolls versus if I just drop
When
it?
it falls.
So is falling going to have a bigger V or rolling going to have a bigger V?
They're gonna have the same.
Fold.
They're
No.
gonna be
Or is it going to be the same?
Falling. It's falling.
Why?
Because you're contributing, since part of it is KR,
Yeah?
you have to have less regular linear V, because only part of it is the KT,
Brilliant.
and you're squaring the V.
Okay, here's the deal. You can make this analogy in terms of your long lost uncle. Okay? So your long lost uncle has a fortune worth $100,000. Okay? And let's say that you are the only surviving heir of your uncle. And he's going to say, hey, you're going to get all the money. Okay? 100,000, it's all you, right? You don't have to split that money. So you could potentially end up with $100,000. In this situation, you get all $100,000 because it's all going to be KT, right? Now, anybody here have a sibling?
Where did you get that?
Okay, Vitor, you have a sibling. Older or younger?
Younger.
Younger. Okay? Brother or sister?
Sister.
Okay. So, at this point, the long-lost uncle says, Vitor, like you, but I'm going to split it between you and your sister. So, in this situation, it's still going to be $100,000, but what's going to happen to the amount of money that Vitor is going to get?
Less.
It's going to be less because he's got to split it. Whereas this way, if he's an only child, he gets all the money, okay? And he can accelerate faster because of the fact he's going to end up with more money. So when something rolls down the hill, this is going to be important. I'm going to have a certain amount of energy, and it's going to get split between my KT and my KR. But if it just goes straight down, it's just going to be
KT.
KT. Louis.
Will it have the same speed, or is that going to be different?
Oh, no. That speed's going to be, that speed here is going to be much less than it is here. Because here, it's all
KT.
KT. Here is KT and KR. So it's the same amount of energy,
Yeah.
but I'm going to split it here where it's all going to be KT going this way.
Okay.
Okay? All right, so Vitor, stop that camera. Let's go back up. Okay?
That's kinetic.
So imagine we had an inclined plane like we just had. Height h, you have a solid sphere, okay, like a baseball, and it's going to be up there, and initially we're going to look at this in terms of this thing rolling down the hill. So when it gets to the bottom, what's it going to have? What two types of energy?
KT and KR.
KT and KR. So this is going to be mgh. That's going to be 1/2 mv squared. And that's going to be 1/2 I
W.
omega squared, right? Okay. Now, at this point, this is just ugliness through and through. Okay, it's bad. It's a train wreck. You can't even begin to solve this problem. But we're going to get clever. Okay? So that's going to be mgh, 1/2 mv squared. So let's start with the fact that we're going to have this I. Okay? So because of the fact that it's a solid sphere, that moment of inertia, I got to remember that, it's 2/5 mr squared. Okay? If it had been a hollow sphere, it would have been like 2/3 mr squared, whatever that is. Because it's a solid sphere, it's 2/5. If it had been a cylinder, it would have been 1/2 mr squared. Now, here's a common mistake that's made. This 1/2 here is independent of that moment of inertia equation. Okay? So don't think this 1/2 is part of that I. That 1/2 was always going to be there. Okay? The whole substitution occurs for that value of I. Okay? That's the kicker. Now, instead of omega squared, what clever substitution can we do?
V squared.
V squared over
R squared.
Oh! Now I can go V squared over R squared. Okay? That's kind of cool. Now, at this point, what's a common term to all of them?
V squared.
Mass.
Oh, gosh.
It's impressive.
Oh,
Oh,
so you're gonna do
Okay.
okay.
so guess what? We can cancel out the
M's.
masses. That's why I didn't give you the mass of the ball. Don't have to have it. Okay? Now, at this point, I've got GH. I've got 1/2 V squared. Now, when I take 1/2 times 2/5, what do I get?
1/5.
1/10.
1/4.
1/5.
1/5. Now, what's going to happen to me R squareds? It's a pirate thing.
Bye bye.
Yar.
R, I'm going to lose me R squareds.
They walk the plane.
They walk the plank. Whoop, there you go.
Here, bro.
So I got V squared, right?
Yeah.
Now, what am I going to get? What's the common denominator of 1/2 and 1/5?
10.
10. So this is going to be
7/10.
5/10 v
1/6.
squared plus 2/10 v squared, which becomes 7/10 v squared. So v is going to equal the square root of 10/7.
GH.
Everybody cool with this?
What a weird number.
Okay? Now, again, here's the dumbest thing that you can do. Oh, every time it's just going to be 10/7 GH. No. Okay?
Bad.
It's bad. If that had been a thin hoop, that would have been mr squared. If it had been a cylinder, it would have been 1/2 mr squared. The process is always the same, but the outcome changes depending upon that moment of inertia. So it's the only thing I have to do to calculate the velocity of that ball. What's the only number I have to have?
Height.
The height. Okay? So let's say that that was, I don't know, 0.2 meters. Okay? So if that height had been 0.2 meters, so somebody take 10/7 times g times 0.2, and then the square root of that.
1.67.
1 point what?
67.
Meters per second. Okay? Now, let's say that I want to actually calculate that value of UG. If I actually wanted to calculate how much energy that I had, what would I have to actually have?
The mass.
Mass. So let's say what I have when I work this out. Let's say that the mass is 5 kilograms. So the mass is 5 kilograms, and H is 0.2 meters. Then my UG would be 5 kilograms times G times 0.2 meters. So do that, what do you get?
1. 9.8.
9.8
Joules.
joules. So that's the value of the estate. Your uncle is leaving you 9.8 joules of energy. Okay? Now that I know the mass, and I also know the velocity, what could I figure out? I could calculate KT. I could figure out how much kinetic energy I have at the bottom because I know the linear velocity. So I could go, okay, my kinetic energy is 1/2 mv squared. So that'd be 1/2 times my mass of 5 kilograms times, what would we get for that velocity? 1.67?
Yeah.
So somebody do that math. What do you get? It's got to be less than 9.8.
Yes.
I think it's around 6 or 7.
Blue.
That's a pretty dang good.
What'd you get?
6.97.
6.97 joules. So if we started off with 9.8 joules and KT is 6.97 joules, how much rotational kinetic energy is there?
9.8 minus.
9.8
Yeah.
minus 6.97, right? Because the total estate is worth 9.8. Vitor is going to get 6.97. His sister is going to get what's left over, right? So if I take that 9.80 joules minus 6.97 joules, what do you get?
2.83.
What'd you get?
2.83.
2.83 joules. Now, at this point,
Yay.
I want to figure out the angular velocity of the spinning ball. So this is my KR. Now, we just said that KR is 1/2 times
I.
I
W squared.
times butt squared,
But
right?
Take the square root
So I take 2 times KR
over I.
divided by I, and then the square root of that's going to get
Rooted.
me omega.
Rooted.
So I got 2.83 joules. But, no pun intended, what am I going to use for I?
I'm gonna use the 2/5 mr squared.
So I got 2/5 times my mass of. Now, at this point, that's going to be times r squared.
Oh.
Now I do have to give you the radius. Okay? To actually find omega, I actually have to give you the radius. So let's say the radius is 0.15 meters, and then that's going to get squared. So to actually calculate omega, you actually have to have the radius of the object. So then you can get omega out of that. Louis,
If you found the velocity beforehand, can't you just divide it by the radius to get omega?
if I gave you the radius of that point. But I just wanted to show you that, number one, that the sum of the energies are going to equal that of.
Gotcha.
Now, interesting thing happens. Out of this, what do you get when you do this math? I want to circle back to what Lydia just said. Do this math, what do you get?
Angular velocity.
11
Radians per second.
11 point what?
2, 11.2.
He's asking for an
11.2?
answer. I didn't. You know, that's
Radians
simple mistake.
per second. Okay?
Where?
Now, if you look at V equals R omega. So let's see if this also works.
Wales is
If I
gonna
take
stop.
that velocity, which we said was, what did we get for our velocity?
1.66.
1.67 meters per second. I divide that by a radius. What did we say the radius was? 0.15 meters. So somebody take 1.67 and divide that by 0.15.
About
You also get 11.2 meters per second.
Wow.
Okay,
Wait, how do you-
I've got both of them have to give me about the same radians per second. Now, let's just say I dropped the ball and didn't let it roll. I just dropped it. If I just drop it, how could I figure out the velocity when it hits?
You know the MGH, and then you would just set that equal to the
Yeah.
KT.
So I know how much energy I had, which was
2 MGH equals 1/2.
9.8
9.8 joules.
joules, right? That's horrible.
It's like
Equals
PB&J.
1/2
PB&J.
mv squared, right? So I've got 2 times divided by the mass of 5 kilograms, and then square root of all of that.
It's about 2.
So what do you get?
1 point. Nah, it's about
No,
2.
it is not.
Let's see. 2 to 9 point.
Around 2.
Divided by 5.
0.18.
No, it's got to be faster than 1.67.
That's about what I said. 3.92. It's about 1.98. Ugh.
Now, here's the deal. Why is
that's
this
19.
velocity bigger than the
Because it
1.67?
doesn't have to share.
okay.
It doesn't have to share it. It's all
It's all.
KT.
all
So
yeah.
it still has the same energy, and this is going to be one of the most important ideas. It still has the same energy. You're just not splitting it.
What?
Okay, so stop that.
how much time?
Old school. Okay, but let's get to that one later.
Well, the one that goes to
So
J.
let me explain what's happening on number 2. So on number 2, you have a pendulum. And then there's like a golf tee here with another piece of clay. Now, listen to me, listen to me, listen to me, listen to me, listen to me.
We're listening.
On number 2, the length of this pendulum is 1.5 meters.
Bob.
The pendulum is already moving. Okay, it's not starting at rest. It's moving at 1.20 meters per second. So what type of energy does it have?
KT.
And
Ugh.
UG. It's going to have KT and UG. When it gets to the bottom, it's only going to have KT.
T.
Keep that in mind. Now, I've also given you this handy-dandy little equation, you all have seen this before, that H equals L times 1 minus
Cosine theta.
cosine theta.
Oh.
So, you have the angle, it's 60 degrees.
Yeah.
You can figure out the height that is in between. So visualize this, okay? So here's a piece of clay that's at rest. The other one's kind of going to come down. It's already moving at 1.2 meters per second.
So you need to add it.
It's going to hit this, and then it's going to become a California problem. And then they're going to move off together. What you're ultimately going to try and find is the angle that that string is going to make when this thing is at its highest point. Okay, that's your end game.
That's a terrible problem.
Oh, it's a great problem. I love that problem. Okay,
It's number 2.
so
So you
let
have to
me
use
give
it
you a
twice.
hint.
So you have to use that L twice.
You've got to use that H equals L1 minus cosine theta. That's going to be your last step. So what you want, let me give you the hint. It's going to be a California problem, right? They're going to move off together. You can calculate the velocity after they move off together using momentum. Then, once you get that, then you can find out how much kinetic energy they have at the bottom. So the kinetic energy they have after they move off has to equal what?
the potential at the top.
The potential of that at the top.
And then you can find the height, and then you can find the angle.
Exactly.
Gosh. Ooh. Horrible.
Exactly. Now, let's talk about number 4.
Oh, talking
So
about
number 4 is the satellite problem. Okay? And it's horrible. I'm going to tell you this straight up. Now, listen to me. Listen to me. Listen to me. On every one of these values, I have given you 3 significant digits. When you write down those answers, you give me at least, Devin Short, 3 significant digits. And let's say you get an answer of 0.01. How many significant digits does that have?
2.
1. The zeros don't count.
Oh, it's only after?
It's only after. If there's a decimal place, you count right. If
But
you write an answer of
Also, we're being Think about
0.01,
it. If you have
Okay.
1, are you counting all the zeros in front of the 1?
so if you get that as an answer,
Are
don't.
you counting all the ones
Now,
after
if it's
it?
exactly, let me give you a hint, which is not going to be, okay?
It's 1.0.
You keep at least 3 significant digits, if not 4, and then round when you get to the end.
That's a mad percentage.
So here's what's going to happen. So this is the ultimate real-world example of what's going to happen on number 4. When you launch a satellite, you have to put it into what's called a barbecue roll. Okay?
What?
Literally, you have to put it into a barbecue roll.
Like the sweet ones?
Huh?
Nah, the sour ones.
The sweet
Like a rotisserie chicken.
The Hawaiian ones.
Oh,
Okay.
the Hawaiian ones are here.
Because what
Hawaiian ones
happens
are
is
fine.
that you want it to rotate, because otherwise one side gets really, really hot and the other side gets really, really, really cold. So this allows an even heating of this thing. So let me give you a hint. This thing is going to be equipped with 4 engines. Okay? It's going to be equipped with 4 engines. So it's going to end up at 32 revolutions per minute. So what are you going to have to do with the revolutions per minute?
Yes.
Change that into radians per second. Okay? It's going to start at rest, and then it's going to speed up.
Yeah.
Okay? It's going to speed up as it goes. So, there is a whole bunch of things that you have to do. Just good luck. That's all I have to say. Good luck.
I'm so glad I took AP.
Oh,
physics.
Mr.
So
Birdcat.
glad.
Now, let me give you a hint on number 4.
You just being some kid. You saw it.
I didn't see.
Because if your answer to 4A is wrong, everything else is
So
going
this
to be
kid's
wrong.
head just caught.
Okay? So let me give you some hints along the way. On number 4A, that answer to 4A should be 0.01 something radians per second squared. Okay? Because literally, if that answer is wrong, everything is going to be wrong.
What?
Okay?
Which one?
So your answer to 4A should be 0.01 and then something after that. Okay? Because if that's wrong, everything is going to be wrong. Your answer to 4D should be something times 10 to the 5th. Your answer to G should be something times 10 to the 11th.
What about
This dude's gotta put
Y?
check
What about
points
Y?
This dude's got to put check.
Checkpoints. I need a save point, Mr. Burke.
Your answer to I is something times 10 to the 14th.
Oh my.
What was G again? I'm sorry.
10 to the 11th.
G was to the
All
11th.
fun and games, you forget it.
Now,
Negative
you
sign
got to
on
go
B.
old school orbital motion problems. Like you got to find like velocity. You got to go old school, like V equals square root of big G M over R. You got to go old school. That's why I said this ties in so many different things.
That was my least favorite unit.
Oh, there
No,
you go.
mine was this last one.
There
yeah,
you
I know
go.
why.
Yeah, that didn't work out well. Anyway,
Poor beats.
there you go.
Bad.
That was a train.
So that'll give you some hints.
that was a bullet train wreck.
What'd you miss?
Yeah, that was a high
That was
speed.
a high speed.
That was
train.
like go right to the heart, man.
That was a head-on collision of two trains right there, between.
That was a lot of kinetic energy right there, man.
Yeah.
Really sold.
That velocity got cubed.
What's the score? Did they score?
Oh,
Not
Why are
yet.
they
Still 1-0.
yeah.
Oh, then the second half.
Yeah. There's 20 minutes left.
It looks like they're like dominating.
Haven't they
us
been
right now.
adding that time though? Haven't they been adding time to the games?
Yes and
Yeah.
no.
They always do.
But it's stoppage time where like if somebody gets fouled, then they like kind of keep track of how much time they were playing.
Yeah.
They add it up here, and then after
Seems
that,
odd. It's like, why didn't you just stop the clock?
It is odd. That doesn't.
It's very odd.
They do
'Cause
that
if
at,
they
like, a high
forget
school
to-
level, too?
No, at high school they stop it.
It's just when it's done, it's done.
Yeah.
well, yeah, if they stop the clock in high school, it's usually pretty serious. They don't like to, right?
Yeah. But that's the thing. Like they don't want to like interrupt.
It's just setting the momentum. Two momentums before, which were 0,
And it makes it more exciting.
equal to two momentum.
Stoppage time does make it
it
exciting.
equal. And so you just set it equal to each other. Yeah.
It's like 0-0.
I still don't know. How do you do number 2? You just multiply them?
I don't know, but in
How
high
does
school,
number
you have
2 work?
further
Bro,
beers,
you
bro.
just multiply
I've been recording.
and